In our last video, we looked at graphing absolute value functions by using technology. Now let's take a absolute value function and look at sketching the graph without the use of technology. So we have the function y equals absolute value of 2x minus 4. So first we're going to determine what the y-intercept and what the x-intercept are. So we'll start by finding the y-intercept. So to find the y-intercept, we want to make x equal to 0. So this is the absolute value of negative 2 times 0, subtract 4. So negative 2 times 0 is simply 0. So we want the absolute value of negative 4, which is 4. So if we want this as a coordinate, our y-intercept would be 0, 4. Next, let's find the x-intercept. So to find the x-intercept, we want to make y equal to 0. So this will be 0 equals the absolute value of negative 2x subtract 4. And this is simply the same thing as saying 0 equals negative 2x minus 4. Now, why is this the case? Well, if you recall, at the x-intercept, both the original function and its reflection will have the same value. In fact, we can show that's going to be the case here. Let me finish solving this first. So we have 4 equals negative 2x. So therefore, we're going to want to divide both sides of this by negative 2. And that will lead us with x equals negative 2 for an x-intercept of negative 2, 0. But suppose we had solved this for the reflection instead. So that would be the reflection of negative 2x minus 4, which would be 2x plus 4. You can see that we're going to get the exact same value. So it doesn't really matter which way we approach it. It's not necessary to do this second calculation, so it's just fine to drop the absolute value bars here when looking for the x-intercept, since we're going to be setting y equal to 0, and these will have the same values at the original function of negative 2x minus 4 and the reflection of 2x plus 4. Okay, so let's just move on from there. That's part A. Part B is sketch the graph. So we're just looking for a simple sketch here. So let me make a very standard graph. We can see that this has an x-intercept at negative 2, 0. And we've also calculated that the y-intercept is going to be 0, 4. So we have this portion to the right of the x-intercept, and we're also going to have this portion to the left of the x-intercept. It's interesting to note here that this is actually symmetrical, and although the question didn't specifically ask us to do this, that also implies that we're going to have another coordinate here, and since the x-intercept was 2 to the right of negative 2, 0, that means that 2 to the left of negative 2, 0 would actually be the point negative 4 and 4. So again, it wasn't asked, but we can use symmetry to label one other point here. All right, part C. State the domain and range. So our domain, this is the possible values of x. So it's x such that x is an element of the real number system. So we can have values of x to the right towards infinity. We can have values of x to the left towards infinity. This graph will continue in both directions. The range does have a restriction though. So y such that y is an element of the real number system. But note that we can't have any y values that are below 0. given that this is an absolute value function. So y must be greater than or equal to 0. Greater than or equal to, because that x-intercept is a valid point on this graph. Last part. Express as a piecewise function. So this is part D. So we want a piecewise function of this graph. Now, it's helpful to know which part of this graph is the original and which part of this graph was reflected. So recall that our graph was y equals the absolute value of negative 2x minus 4. So what does the graph of y equals negative 2x minus 4 without the absolute value sign look like? Well, it's going to have a y-intercept at 0, negative 4. It's going to pass through the same x-intercept. So this is what that graph will look like for y equals negative 2x minus 4. So if we note, the portion to the left of the x-intercept is the same for both the original graph and for the absolute value graph. But the portion to the right of the x-intercept is reflected from the graph of y equals negative 2x minus 4. Alright, so our piecewise function, it's going to act the same way as the original graph, y equals negative 2x minus 4, when x is less than or equal to negative 2. But when x is greater than negative 2, this graph gets reflected. So to reflect it, we're going to multiply through this by a negative, so that will be 2x plus 4. So y equals 2x plus 4 when x is greater than negative 2. And that is the piecewise function for this absolute value function. Now, exercise 2. Write the piecewise function y equals the absolute value of 3x minus 5. Let's try and get there by doing the minimum amount of algebraic work. One thing we will definitely need is the x-intercept. So let's find that. So we want to find the x-intercept, so we're going to make y equal to 0. So we get 0 equals the absolute value of 3x minus 5. So we can just say 0 equals 3x minus 5. This gives us 3x equals 5, and therefore x equals 5/3. So we have an x-intercept of 5/3 and 0. Now, I said I wanted to get there by doing the minimum amount of algebraic work. So let's see. We have an x-intercept, 5/3 and 0. What do we know about the original graph of y equals 3x minus 5? Well, it's got a positive slope, so we know it's going to be going in this direction. It's pretty easy to actually look at this graph and see that the y-intercept is going to be negative 5, but again, minimum amount of work. What's our absolute value function going to look like? Well, it has to be positive, so it's going to look something like this. So we can reason that on the right-hand side, these two graphs are going to act exactly the same way. On the left-hand side, this graph is a reflection. When I say right-hand side and left-hand side, I'm talking about in reference to this x-intercept right here. So let's write this piecewise function. Y is equal to the original function, so 3x minus 5, to the right of that x-intercept, so when x is greater than or equal to 5/3. And it acts like the reflection, so negative 3x plus 5, when x is less than 5/3. So I mentioned that this is the minimum amount of algebraic work. This sketch certainly does help to reason it together. One might say it's probably optional as far as work, as long as you can visualize the original graph, but it certainly helps to tie things together, and it makes it very clear where this piecewise function is coming from. So that is graphing linear absolute value functions. In the next lesson, we'll look at graphing quadratic absolute value functions algebraically.